Algebra 1. Today we are learning Lesson 21, which is Predicting Populations. First we have a notice and wonder, and I love notice and wonders when we're in the classroom because everybody gets an answer and everybody's answer makes sense. And notice and wonders when we are distance learning is kind of stinky if you ask me. All right, I'll notice and wonder. Let me get my highlighter pen out. Let's see. That's my dog snoring again. Population of Paris looks to be growing kind of slow. Okay? I mean, not a ton of growth back there. Where I look at Austin, looks to be booming. Okay? Much faster growth. And Chicago? Chicago got smaller and smaller and smaller. So there's my notice and wonder about those. That's sort of my noticing. My wondering is, why is Austin growing so quickly? It's hot in Texas. I don't know who'd want to live there. Let's see. What happened with Chicago? Why did Chicago decrease in population? Okay, that's my wonder. Let's see. Paris? I don't know. Paris is huge. Do you think Austin will ever get as big as Paris? I wonder. I know, noticing and wondering is never the same without all of you guys in the classroom. It really is much more fun then. All right, here are population data for 3 cities at different times between 1950 and 2000. What does the data tell us, if anything, about the current population in the cities or what the population will be in 2050, 100 years later? How would you describe the population change in each city during this time period? Write 1 or 2 sentences for each city, then discuss with your group. Okay, I'm going to get a new piece of paper. Or a new piece of whiteboard, right? If I were to look, let's see, I have Paris. Paris population is increasing. That's what I would write. But it's increasing slowly. That's what I notice. Okay, if I look at Austin, again, this is just the answers for number 1. The population is increasing. And it seems to be increasing quickly. Or quicker. I guess we could say quicker. Quicker as time goes on. And then Chicago. Poor Chicago. Okay, the population is definitely decreasing. If I look at, I'm looking at the table too. I guess in between 1990 and 2000, it increased again. I really do wonder why. Let's see. I'm not sure about the rates of increase or decrease. It hasn't really told us to calculate that yet. I'm probably getting ahead of myself, aren't I? So that's something that will help us analyze the 3 cities a little bit better if we could compare the rates of increase or decrease. Number 2, what kind of model, linear or exponential, or both, or neither, do you think is appropriate for each city population? So these are number 1. If I look at number 2, let's see. For Paris, I have to look at the table on my computer. I'm going to do the differences. I really would ask you to work along with me. I'm going to look at the differences for each year. Let's see. Successive differences. If I do 74 minus 63 That is, oh, so many zeros. Okay, next would be minus, nope, backwards. 82 minus 74. And that's going to equal, so my increase is decreasing, right? If I subtract the next two, I get 500,000. If I subtract the next two, I get 600,000. So they're not consistent, but I wonder if they're close enough. That's Paris. So linear might work because they're pretty close. My successive differences are pretty close. They're not constant. They show they have the same general trend, right? Little more than 500,000 per year, give or take. You probably could argue that maybe not. But if you decide not linear, you would need to calculate the growth, the factor between each one. So if I take, let's see, look at my chart again. 1, 2, 3 over 63, 0, 0, 1, 2, 3. I get 1.07. And for each of these, I get, if I kept going, I get a factor of about 1.07 each. Okay, so we could argue that exponential would be okay too. Okay, with that being so close to 1, again, you could argue either way, but with this growth being so close to 1, I would still probably point back towards a linear model. Okay, all right, let's move on. Still on question 2. I know. If we looked at Austin, linear model's not appropriate. So first we look at the differences by subtracting them all. And I would ask you to do this along with me. So as you calculate Austin's difference, these values keep getting bigger. Each difference you would calculate. So linear is not appropriate. If our differences aren't somewhat equal, then linear does not work. If we do our factor, we would say 187 over 132, and then 254 over 187. If we kept going, we would get a factor of about 1.36 to 1.42. Okay, somewhere in there would be our factor for Austin. Okay, not all the same, but pretty close to each other. So we are definitely exponential with Austin. Then if we looked at Chicago, first we look at our differences. The population is decreasing for most of the period, but then it increases. So the successive differences are not that close. I'm not going to bore you with my calculations again. even though I wasn't doing them anyway, wasn't doing them all. So not that close. So linear isn't the best. If I keep going with Chicago, we could draw a line connecting the initial and the final population, because remember, we decreased then increased a little bit. So if we drew a line connecting them, this overestimates the population for much of the time. Exponentially decreasing isn't appropriate. So really, this one is a big old question mark. Linear doesn't work. Exponential doesn't work. It's just a big old mess. We are using a lot of whiteboards for this one. So we just did question 2. If I look at question 3, it asks for each population that you think can be modeled by a linear or exponential function, write an equation for the function, and then graph the function. So when we looked at, I hope you guys are taking notes. I guess I should have told you to do that, but you can always rewind. When we looked at Paris, I think we decided linear because our successive differences were pretty close. I had a successive difference of 1,100,000, 800,000, 500,000, 600,000, and 400,000. Okay, that was the differences. If we did exponential, our growth factor was about 1.07. So we'd really want to look at our initial population, which was 63 or 6. Go back to my chart. 6,300,000. And we're going to be adding to that. And what we add to it is really an average of this. So if you add all those together, you get about 700,000. And that's our slope. Where D would be decade past 1950. If we looked at Austin, our initial population was 132, and our growth factor, let me look back on my slide, what did we calculate? Somewhere between 1.36 and 1.42. If I just average those, I get 1.39. So that's going to put what we put in here, raised to the D, where again, D is the decades past 1950. And then Chicago, can't do it. I can't model anything because we decided it wasn't linear and it wasn't exponential. As far as graphs go, I would honestly just be putting those into Desmos. Right? You guys can do that. You're super smart. I think we're on number 4. Yep, compare the graphs of your functions with the actual population. How well do the models fit the data? I'm going to plop a document in your Google Classroom with this information. Cool. Okay, distance learning is not fun for this one. I would definitely have a show and tell with this one if we were in class. And then number 5, use your models to predict the population of each city in 2010. So Paris, I had P equals 6300,123 plus, what was the rest of my 700,000 D. So D is going to be 60. in 2010, right? And then D is going to be 100 in 2050. Excuse me. In 2010, looks like I'd have 10,700,000. In 2050, 13,300,000. Okay, kind of impossible, but models aren't always the best. If I looked at Austin was, what was my equation? 132 0 0 0 1.39 1.38. I can't remember if I had 38 or 39. I'm sorry. I'm going to raise it to the 60th power, and then I'm going to raise it to the, so first we're going to raise it to the 60th power, then we're going to raise it to the 100th power, and that gives me 912,000. Haven't reached a million yet. And then 3,300,000. I'm not sure that's possible either. Pretty cool. And then Chicago. I can't do it. No hope. So the last thing here is, do you think these predictions can be accurate? I don't know. I think Paris, because Paris is just linear, is very possible. Can be accurate, but an exponential function always goes a little too crazy there at the end. That 3,300,000 people in Austin is probably not possible. All right, that's actually it. I'm not going to do the last slide. I think we've talked a lot about functions, and the lesson's getting a little long, so it's okay. I've looked at our final assessment, and I think we'll be fine. But we'll talk later, okay?